although I have had the pleasure of working with Sylvia now for many years, she may be a new face for some of you on the call. I had the great privilege of working with Sylvia at Intel for many years, and we have both recently departed and taken on the world of more independent consulting. So that's actually the affiliation you're seeing for Sylvia. Her new LLC, she may be able to tell us a bit more about that. But it's a wonderful pleasure to be able to invite her to this audience, because I haven't had the privilege of having an actual engineer speaking in this series, which seemed really, really important. And Sylvia is a senior principal engineer and an AI architect with extensive experience inventing, standardizing, and bringing new technologies to market. She has over 30 years in high tech, and her specialties include quantifying and reporting Scope 3 downstream carbon emissions for compute systems, multi-modal AI sensing in presence detection, noise suppression, and transcription, and low power graphics, media, HDMI, DisplayPort, and HDCP. This is a really exciting moment where we get to hear a little bit of Sylvia's thinking since leaving. In fact, one of those software teams that Bernadette was just mentioning, one that was supposed to be charged with an open source agenda, but it was becoming difficult to see how that was likely to continue. So anyway, I have asked Sylvia to give us a more technical talk than we've had so far in the series, precisely because there's no one better I could really ask to explain some of the steps in the decision-making process that goes in software development and AI. So over to you, Sylvia. Thank you so much for joining us and for being willing to share some of your insights with this audience. And we have you until the top of the hour. So plenty of time for questions too, if they come up. Thanks.
Wonderful. Well, thank you so much for a very generous introduction, Mel. Let me just... So, as Mel mentioned, I have decades of experience at Intel Corporation, and I was really fortunate to be there during times where that were very exciting for computation, ranging from computer graphics and flash memory and AI all coming to fruition. But actually stepping back for a minute and remembering our acknowledgement of place, I like to open my talks with a picture of some place that I've recently visited. And so this is from Baja, California. I was really privileged to be in the ocean when humpback whales were going through their mating cycle. This humpback whale was breaching for maybe an hour and a half. You'll notice that it's got a lot of barnacles on it. I don't know if that means that it's old, but or mature, but there's in the lower left-hand corner of the picture, there's a gull that you'll notice, and that was following the humpback whale. I was just fascinated by it. And the guide told us that what happens is that the barnacles fall off of the humpback whale when they breach, and the gulls come and eat it. So everyone benefits from the big player doing big things, but the gull is just feeding off of that. So as Mel mentioned, I'm assuming that most of the people in the talk today are not data scientists and have not necessarily brought an AI solution to market. And so I'm going to be going through kind of the nuts and bolts of how we brought things to market. It's not the only way, but it is representative of what you'll see in the industry. And I think hopefully you'll what I'm hoping to give you is an idea of how you could influence implementation of AI solutions in the future for good. So this is the problem statement as I see it, right? We have this idea of this nameless, faceless entity that is in danger of consuming the world as we know it. And here, what I'd like to be able to do is show you a little bit more detail on this AI side. In my role as a senior principal engineer, I led a team of architects, and what they did was actually write the specifications for other people to implement integrated circuits that accelerated different functions in hardware. Okay, and today we're going to be talking about speech recognition in particular, but it really is applicable to a lot of different areas as well. So with that, one of the things that you need to keep in mind is that engineers thrive on requirements and understanding what's expected of them. And like anybody, any humans anyway, people act according to the way that they are rewarded. And they're rewarded for actually fulfilling their requirements. And if you would like to influence, one of the reasons that I've worked on so many standards is that it's not only a way of establishing robust requirements for engineers, but it also influences the industry and influences worldwide implementations of technology. So, so with that, let's talk about neural networks. I will say, you'll notice that Cindy was talking about machine learning earlier. Machine learning is a larger topic of a larger description of artificial intelligence. A lot of what people have been implementing lately has been concentrated on neural networks. So neural networks are a computational structure that are meant to mimic the way that neurons work in the brain. Okay, so you'll have some kind of input. So we're talking about speech recognition in this case. So it would be sound as the input. And there's computation that's done on this input, and there's an output based, providing a result based on the calculations in the middle of it. So the computations are done on what are called neuron points, like I said, mimicking the function of the brain. But the actual computation that's done in these hidden layers is very, very simple. It's multiply, accumulate, or adding, and what's called activation, which is kind of curve fitting or kind of snapping to a number. And so I will say also, the reason that a lot of people use graphics accelerators for neural network computation is that this is very similar to the kind of math that's needed for 3D graphics. So there's a lot of multiplication and accumulation and activation within 3D graphics. So now so you'll hear people talk about layers. So there's the input layer, the hidden layers, and the output layer that's the result of sending the input through these hidden layers and computing the result. In training, so what a data scientist will do is they'll guess at what math has to be done at these hidden layers, and it's wrong. It will never be right in the first iteration or the second iteration or the third iteration. So they go through very many iterations of adjusting the parameters in the hidden layers to create an output that's more accurate given the input and the result that they want. Okay. The act of inference is once a model is trained, given any input, it will create an output, right? So you may have, for speech recognition, for instance, you may have trained a model given a transcription of a TED Talk, right? With all of the vocabulary that's in a TED Talk and all of the input that's in a TED Talk, and you've got the output, and it's fairly accurate based on this database of TED Talks that you've trained for, right? When you use it for inference, we may be using it for a Zoom call like we're having here for transcribing what I'm saying to you right now, as an example. So I should say also that the power consumption is roughly tied to the number of elements in the network. So you'll hear model size or number of parameters. And what that has to do with is the number of calculations that have to be done in order to create an output. So with that, this is an example of a classical speech pipeline. And this was in use for very many years. If you have on the left-hand side this person saying hello world, their vocal cords and tongue and cheeks and, they are producing a sound, which is made up of that vibrates molecules in the air, okay? And the microphone picks up those vibrating molecules and translates them into frequencies, okay? So you take the physical vibration and make it a frequency. So for instance, a concert A that the oboe uses to tune an orchestra is 440 hertz, 440 vibrations per second. And so the frequency representation of that is 440, okay? So a person's voice is actually made up of several frequencies. So the frequency representation is a bit more complicated than that. But that goes into the next step, which is called acoustic scoring. So if someone says hello world, then the acoustic scoring creates the phonemes, which is to say the small sounds that make up these words. So there's lo world, these smaller pieces of sound, and those phonemes get fed into a step that's called vocabulary. So that you combine the sounds into words and the words into word sequences, and the output is word sequence. The word sequence goes into an application, and depending on what the application is, it creates some directive for a response or some kind of result that comes back. And let's just say that it's a word sequence. So for instance, if this person is saying hello world and it's just waking up the application, then the word sequence coming back may just be saying, how may I help you? It goes through sound generation, which in and of itself is also another science. So there are things like the tone of voice and the ups and downs and prosody that sound generation involves. And that ends up as a frequency representation that goes out to the speaker and says, may I help you? Okay, so for each one of these orange boxes, there's some kind of calculation that happens, okay? And before 2012, it's a series of various different, I'll call it arts. So on the signal processing side, getting a signal and creating, deciding what to pay attention to and what not to pay attention to, what's background noise, what's words versus what's music, right? That's all done with filters and signal integrity techniques that took decades to develop. The acoustic scoring was done with a Gaussian mixture model. Now, the first accelerator that I worked on was called the Gaussian and Neural Accelerator, or GNA. And so originally, you would take these frequency representations and combine them to create phonemes using a combination of these waveforms, right? And that's what this Gaussian mixture model is. And then for vocabulary, we had a hidden Markov model, which involves a Viterbi search. So this is a machine learning technique. Given an input, what are the probable outputs, right? But it's a search algorithm, right? And then all through the application and the response generation, depending on the application, those may be different. But then again, on the output, you have that same kind of signal integrity and filtering that goes out to the speaker. So the success metrics here, and I'm getting back to, the way that people act is according to how they are rewarded. The success metrics for a pipeline like this were latency and accuracy, definitely. So latency means from the time that someone says hello world to the time that you get the word sequence that goes into the application, how much time does it take, right? And then accuracy, and that is actually one measure of what they call performance. And then accuracy is measured in many different ways for speech recognition, but one key way was called word error rate. Okay. So in other words, given what someone said, how often would your word error rate be correct? Now, I will say that as humans, the claim is, and there's different background information on this. The claim is that humans are 90% and 96% accurate. So we've got a 4% word error rate. Now, however, it's context actually that helps us get things right. So no one's perfect. I should mention here also, because we're talking about sustainability, power consumption and the model size. We're really only a consideration when it's integrated into a system. So the model size has to do with how much memory is available, for instance, and how much time it takes to actually access the memory, right? Because that impacts the latency. And then the power consumption, sometimes it's a constraint and sometimes it's not a constraint. So with that, keeping that in mind, there was a really important paper, article, I should say, published in 2012. So if you're older than 12 years old, you may remember that speech recognition was terrible maybe 20 years ago. And all of a sudden it got better. So this has a lot to do with that. So the pipeline was the same, but there were several companies that got together and did some research to show that if a deep neural network was applied to acoustic scoring, then the error rate for the same training data, the same amount of training data, would reduce by 30 to 50%, depending on the data set, or it would reduce the amount of training data that was needed by 7x compared to a Gaussian mixture model. So this is where, from the person saying the words to the word sequence out, given everything else the same, applying a deep neural network, which is to say one that's more than 2 layers, more than 2 hidden layers, gave this drastic improvement. So everyone started using this. So I started working on speech recognition in 2016. And at that time, everyone started working on this. And if you looked at the size of the model for acoustic scoring plus vocabulary, it was somewhere between, it was more than 500 million parameters that people had for a large vocabulary, plus acoustic scoring, which is big. It's a lot to store in a system if it's a local system. And then what happened was that while I was working on this, people started trying out deep neural networks on everything. Okay, so we in the US we talk about if you throw the spaghetti against the wall, it's done. And so if you're just trying something, you keep throwing the spaghetti against the wall. Well, the deep neural networks were the spaghetti that everyone was throwing against the wall. So in this case, people started using a deep neural network for signal cleanup. And actually, our Gaussian and neural accelerator was first used not for acoustic scoring, but for removing background noise from phone calls. So for instance, if we had a dog barking in the background, it completely eliminated that background noise. Okay, and it was very useful, especially when COVID hit, right? Not only that, people started combining different steps in the pipeline together. So acoustic scoring and vocabulary ended up being combined into a single network. And so it started being just the fashion that everyone started using deep neural networks for various different steps in the pipeline. And also, I want to call out that this deep neural network that was applied to acoustic scoring plus vocabulary ended up with a model that reduced by, in the time that I was working on speech recognition, 25x, right? So you can also imagine that the power would have gone down as a result of this too. So now the reason that people were trying to get the model to be smaller is so that they could fit it in the system that they were working on. Okay, so it became a requirement and people worked on it and it got better. So that's a teachable moment. Okay, I'd like to talk a little bit from shift gears and talk about the development flow. Bernadette mentioned open source. Open source is a huge, huge benefit to anybody who's working on algorithm development. What typically happens is that if somebody wants to develop an algorithm, they refer to prior work because it's really hard to start from scratch. So what they do is they go to somebody's published GitHub, they get the code, they try to recreate it. They do this all with a CPU. And once they've recreated results, so they have to train a model, they have to get it going. This is an iterative process. And then they have to adjust it for their own use, right? They may not be using it for the same reason that someone wrote it in the first place. After that, you have to integrate it onto an accelerator. So it needs to be compiled for, if you're using an accelerator, it has to be compiled for that accelerator that has its own instruction interface and own language. And then you have to check the accuracy and the performance again. And sometimes it doesn't work the same. Even though the math is supposed to be the same, there are differences in compilers. Something that you used for the CPU could be slightly different than what you're using for an accelerator. And so you may have to go back to algorithm development again and iterate, okay? Then once you have incorporated into an accelerator, if you're using that, then it needs to be integrated into a system. So for instance, let's say we're talking about a web search again. There's already a given flow that has been in use for web searches. So this algorithm has to be incorporated into an existing application. And that means that there are things like handshaking requirements and latency requirements. And there's just certain expectations of how it's going to fit into a system. That's also where you have constraints about how fast it's accessing memory. And what if it's accessing memory while something else is trying to access memory? And you have to manage the resources within a system. Okay, so that may, if that doesn't work out the first time, you may have to also go back to algorithm development, right? So you can see it is a very iterative process and it's very painful. So changing an algorithm after it's already been deployed is a lot of work. You'll hear a lot of people talking about federated learning. So in other words, learning on the fly and updating your model on the fly. The validation of that is probably one of the hardest things, in my opinion, if you've already deployed a model. So with that, let's talk about consumption. And I should talk about not just power consumption, but also resource consumption. So an implementation of this pipeline, we're back at this speech pipeline. An implementation can be local or remote. So you can contain this entirely in a system, or you could, there are very good reasons for someone to want to do parts of this task on a server because they'd have a single point of deployment. They can update just on the server. There's a lot of reasons that somebody might do that. However, it doesn't just because you run on a server that is in Iceland running on green energy, for instance, your data has to get there somehow. So here what I've shown is some kind of transmitter and some kind of receiver going to and from a cloud. Now, each one of these orange boxes may or may not be done in a single server. It could be done in more than one place. But, and also you could have one or more different things in the pipeline, local or remote. So, but when you're transmitting from wherever the person is using the technology to and from the compute resource, it's often going thousands of miles. And that means you don't have just one base station that's transmitting something. You have many that are. And the way that they are built is they're always ready for action because they need to be, and this kind of ties in with Cindy's talk here, they need to be limiting the amount of latency between somebody saying something and getting an answer, okay? So it is quite consumptive to be going to a server. And in fact, we one of the things when we were working on metrics for software, one of the things we were trying to do was call out this transmission cost, and we did not get there. Okay, so that's still to be done. So if you think about this, we talk a lot about training and how consumptive it is because it is really obviously consumptive. I looked for different sources. Juniper Research had a nice study that estimated in 2020, a few years back, that by now 8.4 billion devices with voice search capabilities would be deployed worldwide. So the amount of power that takes is, of course, the number of users times the number of invocations times the average power per invocation. And I claim that the number of training iterations is far less than the inference iterations, and it can travel thousands and thousands of miles. Now, I will say with respect to audio data, it's not very rich compared to video data. So I did want to just talk about video for a moment. So that pipeline that we just reviewed for audio, there's a similar path for video. So you have some kind of input from the camera, say for instance, this video conferencing that we're doing now. There's signal processing, and I'll call it, if we're compressing into MPEG, for instance, that's a really common broadcast format. And then it gets sent to an application, and then there's some kind of response. So for instance, I'm sending a picture to the Zoom server, and then it's also giving me back a picture of myself and a picture of Mel and a picture of Cindy, so that I can see, myself and what's going on with other listeners on the line. And it can be transmitted remotely at several points in the pipeline. So that pipeline has different opportunities for where you can transmit data to a server. But the data rates on video are many orders of magnitude higher than audio. So I just did back of the envelope calculation, and for that same MPEG-2 stream, nothing fancy, 5 seconds of typical video, there's something like 200 million bytes of data. And same thing with typical audio for telephony type of purposes, is about 200,000 bytes. So video is definitely much more consumptive. So thank you for keeping your camera off unless it's necessary. So I've made all of the points that I was going to make here, but I just thought I'd reiterate. AI is math that's applied to solve new and existing problems, but it does have to fit into an existing framework almost always. The success metrics have focused on accuracy and latency, but if developers are rewarded for the efficiency, they do respond. And then once they're done, if they've met a requirement, they stop working on it. One thing that I didn't mention is why the model didn't get any smaller after it reduced by 25x. It's because it fit in the system, so it didn't have to reduce anymore. And then I'd suggest viewing the problem as a computational consumption problem rather than just AI in itself, because AI doesn't exist in itself without the rest of the computation. And if it's not AI, it's going to be something else that gets developed. And the highest impact is in intercepting the problem statement and engineering decisions when you're starting to work on the problem rather than after the fact, because it's just so painful to change these systems.